Hi guys, welcome to today's lesson. So today we're going to be doing some Euclidean geometry. The very first lesson that we are having today will be an investigation of what it means to have circles and lines, right? So you know that Euclidean geometry is all about circles, it's about angles, it's about quadrilaterals, which we're going to talk about at a later stage. But for today, specifically, we're looking at circles and lines. But let's start with our mind map just to see exactly where we're going to start and where we're going to be going with every particular concept that we're going to be talking about in terms of Euclidean geometry. So let's start with that. So firstly, remember we're talking about circle geometry. We know that even though I say it's circle geometry, there's circle geometry in analytical geometry, but in specific, we're talking about the Euclidean geometry. So here we're going to be looking at lines, which I just said right now, and the types of lines we have, they have a relationship which we normally claim is perpendicular. At times, some line is called a radius, some line is called a chord. I will then go into great detail of all of these. There's a line that is called a tangent, which we're going to talk about in great length at a later stage. Also, if lines are four of them and they are joined together, we then call them a cyclic quadrilateral. You know, a quadrilateral would be having four sides. We're also going to be looking at the concept of angles at a later stage. And then with angles, there will be alternate segment, same segment, at the center, and some right angles. So these are all the things that we're going to try and talk about, specifically looking at the concept of Euclidean geometry. But now, remember, we always start with a very big question that I want you guys to think about. Is it possible for us, one, to construct a right angle using only a compass, a ruler, and a pencil? So this goes back to the founder of Euclidean geometry, Father Euclid, because when he did all of these things, he did not have all these fancy things that me and you are having today, a protractor that you can calculate an angle, a ruler maybe that has numbers and all of that. He did not have all of those. What he had was a straight edge, which right now we call a ruler, and a compass. And he did a lot of constructions that actually we then claimed were theorems at a later stage, and then we are using today to try and find all those angles and lengths and shapes and all of that we are doing today. So can we do that with only those things? Meaning, you don't put a protractor to try and measure a 90-degree angle. No. Can you then use these three things, a pencil, a ruler, and a compass, to try and construct a right angle? Try it as you are busy thinking about it, and let me know what you think about it. But for now, let's just go into the investigation of exactly what it means to have a right angled triangle or a right angle in any shape. But specifically right now, we're going to be looking at in terms of a circle. So here, our keywords will be a circle. Remember, a circle would be a locus of points that are all equidistant to one point. So when I say locus of points, I'm talking about the circumference of the circle, because the distance there, remember from earlier grades when you were doing this, the distance there will always be the same throughout. Hence, we call it a locus of points. And that distance we then call the radius of the circle. We also have what we call the diameter. That's a line from one end or one point on the circumference through the center to the other side of the circumference. Also, we have a chord, which is from one point on the circumference to another point on the circumference. It doesn't have to pass through the center or anything like that. But now in specific, let's look at what exactly is a circle and the parts of a circle that we have. We have what we call a radius, and we normally use R to depict a radius in a circle, right? Radius, you know, is the length from the center to the circumference of the circle. And what we know is this will always be the same throughout our circle. No matter where you are, as long as you are moving from the center to the circumference, this will always be equal. Also, we have what we call the diameter. Now, with the diameter, remember I said it's from one point, so I'll say this is A and this is B. It's from A up until B, but the condition is that it must pass through the center of the circle. We then call that the diameter of the circle. But now, the relationship that you need to know between these two lines that I have on the board right now is that the radius is normally half the length of the diameter, meaning the diameter is 2 times the radius. So this is R, that is R, and then in total, this will then be 2R. So if my radius is given as 5 centimeters, it means my diameter will then be 10 centimeters. If my diameter is given as 20 centimeters, it means my radius will be 10 centimeters. So that's the relationship between these two lines that I have. We also have what we call a chord, right? Now, a diameter is also a chord, but it is a special kind of chord because it passes through the center. Hence, we then give it the name diameter, but it is also a chord. A chord, the definition will be, it's a line from one point on the circumference to the other point on the circumference. Any point for that matter. I can draw it like this. It doesn't really have to be on top there. I can draw it like this, and I can have it as small as that part there. That's the chord of this particular circle. The other thing is that you need to know about a chord is, at times we're not going to give you the line. I'm just going to give you 2 points on the circumference, A and B, without joining them together. But because you know that a chord is made up of 2 points that are on the circumference, we then going to call it the chord as well. Though with a chord in specific, if we define it, it needs to be a line. So at times, just note that you will see at a later stage, you won't be given that line. You will only be given the 2 points, which will then show us that there is a chord that we have there. Because remember, to form a line, you need a minimum of 2 points. So that's what you need to know about that. Now, the investigation that I said we're going to do when I started is when a chord and a radius intersect with one another, right? So I have a circle like this. There's my center there. I have the radius there, and then I have my chord there, right? And they are intersecting, let's say, at point A. Is there a relationship between the angle formed, meaning the angle that is between this chord here and this radius here? Is there a relationship between that? And also how the radius cuts the chord, right? Is there a relationship between that angle? So maybe if I say this angle is 30 degrees, does that tell me anything about how the radius will cut that particular chord or not? That's what you need to be thinking about, right? Into different lengths. So does that make this maybe 2 units if we know what the length is, or this one 6 units, or does this become 5 units and that 10 units? What is the relationship between those that is there, given that we know the size of the angle that is there? That's the investigation that we're going to try and do right now. Now, I have a circle here. You can see there's a way of moving all these points on an app called GeoGebra, but at times also Sketchpad, even Google, you can try and look at what this particular shape is all about. We're going to be trying to move points and see what is it that we're going to be seeing in terms of the length and the size of the angle. And then at a later stage, we'll then draw a conclusion based on that investigation. So firstly, I want you to move the point B along the circle until it gets close to point E, right? But while moving that point, what you need to pay close attention to is angle BDE, and the length of BD with DC. Right, so let's go back to our shape. So you need to look at closely this angle that is here. What is happening to that angle as you are moving this point here closer to E, right? Because that's what it said. Move along the circle until it gets closer to point E. So I am moving it in that direction. You need to look at what happens to this angle. Also, you need to look at what happens to this length here with that length. What is the relationship between the two? Because remember, the big idea here is we want to know what is the relationship between this angle and how the radius cuts the chord BC in this context. Also, the other thing that you need to try and do is to move the point D again in the opposite direction, right? Until point D gets closer to A at the origin, right? Which is the origin of the center. So you also need to try and move this until this point here is it is on top of point A, and try and talk about what exactly happens in terms of the relationship. So now we're moving it in that direction. We're also looking closely at what happens to this length with that length. This is 4,75, that is 5.2. We look at what is happening to those lengths, right? And as maybe if I was to just show you an example, if I move it to there and now my B is there, clearly you can see that the length of BD will be a bit more than that, right? Because it's now a bit bigger than what it was when we were here at this point. So maybe this can turn to 5, right? But as this is turning to 5, what happens to this one? You need to look at that. This one will then be smaller than what it is right now. So maybe it will go to 4,9 units. That's what we need to be thinking about. And also this angle here, as I am moving it that way, what happens to it? It will then be greater than what it is right now. That's what you need to be thinking about to try and see what exactly is the relationship between the two. The other thing that you also need to try and do is to then move point C now towards E, right? And then in the opposite direction. But also remember, we're still looking at the very same thing, the size of BDE, the length of BD and DC. So we're moving C towards E, you're moving point C towards E that way, and you're also moving it in the opposite direction. Try and see what happens to this length and what happens to that length, right? And also try and see what happens to this size that we have there. So will it be a case where if my angle is 81.95 degrees, the size of DC will always be 5.2, the size of BD will be 4.75. We don't know as yet. We are going to try and draw a conclusion at a later stage. But you just need to think about that, to say, is there a relationship if the two lines are intersecting? It doesn't matter how they are intersecting, right? As long as they are crossing each other. Remember, to intersect means to cross each other. As they are crossing each other, is there a relationship between this angle that gets formed between the two lines and how the radius, which is the line from the center to the circumference, cuts the chord that we have at that time? That's the main idea that we're trying to investigate here. And then at a later stage, after the conclusion that we're going to draw, you will then see where exactly this is going in terms of it being a theorem that Father Euclid actually discovered years, centuries back, even not even just to say years, it's centuries back, because this thing has been there for a while now. So that's what I want you guys to please think about there. So mainly the big idea that we are having here is I have my circle there and I have the center there. If I draw a line from this center to the circumference there, we know we call this the radius. And then if I draw a line from one point to the other point on the circumference, which is my chord, is there a relationship between this angle here and how this line, which is the radius, cuts this particular chord that we have there? So will these have a ratio to one another or not? Will they have any relationship for that matter? Will they be equal? Will one be twice the other? Or will they just not have any relationship for that matter? That's what I want you guys to please think about. But for now, I will leave you to think about it, and then we'll go to an ad break. When you come back, we'll see exactly where this is going in terms of everything that I've just spoken about. I'll be back just now. Hi guys, welcome back. So I hope you tried to investigate what we've been talking about before we went to the ad break, right? We looked at what happens when I move a point around, right? That moving of a point is all about trying to see what the relationship is between the angle that is formed in between the two lines, the radius and the chord, and also how the radius cuts that particular chord. Now we're going to try and draw some conclusions based on that investigation. And then one thing that makes us one of a kind as mathematicians is that we always have a proof for everything that we're talking about. After all, you know that mathematics teachers always say they've got problems, but our problems always have solutions and they always have proofs. So we're going to try also and look at a proof of what exactly is it that we're going to say in terms of a conclusion, and what happens when now we twist it around. Is it still true or not? So that's what we're going to be looking at. But for now, let's just look at our mind map and try and see what we've looked at so far. Right? So far we looked at the concept of a radius, which we said was a line from the center of the circle to the circumference of the circle, and then we said twice the radius then gives us the diameter of the circle. We also had the line called a chord, and a chord will be a line from one point on the circumference to the other point on the circumference. It doesn't necessarily need to pass through the center, right? When it passes through the center, we no longer call it a chord. It has a special name, which we said is a diameter. So please remember that. Now, we have what we call a conjuncture. Now, I said to you, what makes us special as mathematicians is that we have proofs. A conjuncture will be like a baseless claim, right, that has no proof whatsoever. So we're going to try and make a conjuncture. The conjuncture will be based on this investigation. What did we see in terms of the observation, right? So as mathematicians, what we do is we observe things and we get fascinated by those observations, and then we try and use some math to prove exactly whether what we are seeing with our eye is always true or not. So that's what a conjuncture is all about. A conjuncture will be a claim that has no proof that supports it or anything like that, is really based on observation and what you saw when you were trying to maybe do an investigation. And then only after when you analyze, you can then have a proof. Then we can call it a theorem, because then now it has a conjuncture, which is what we saw with our eye when we were trying to do that, but now it has a proof. Then it qualifies to be a theorem. But if it's only an observation, really, remember they always say looks are deceiving. So make sure that you understand this. Now, the summary of the observations that we saw with that particular thing that we're doing is that when the angle between the radius gets close, right, the radius and the chord gets close to 90 degrees, we saw that the segments of the chord are equal in length, right? So if I have that center there, the radius there, and I have my chord there, if this angle becomes 90 degrees, the conjuncture of the observation is that those two line segments there become equal to one another. So that's what we are at the moment. We're going to try and prove this if it does really exist or not. We also have what we call a converse. A converse is to say if this that I have is true, if it is perpendicular to one another, it means that this line and that line are equal. The converse will be if this line and that line are equal, it means the two lines are perpendicular to one another, right? So if this line segment here, let me just maybe draw it this side so you can see exactly what I'm talking about. The converse of the same thing we are talking about here is if this line is passing through the midpoint, right? Meaning it is cutting this line, the chord into two equal parts. It would therefore mean that it is perpendicular to it. That's what the converse is all about. So when the radius intersects with the midpoint of the chord, that's what I just said, then the angle between the radius and the chord is 90 degrees. That's what the converse says. It's another conjuncture, but you must remember that because it's an observation that we have. After all, with an observation, remember, guys, if I say it takes 20 kilometers to get to the mall, I can then say to get to the mall, it takes 20 kilometers, right? So I can tell you how long it takes to get there. Also, I can say if I want to go to the mall, it means that I must then walk or I must drive 20 kilometers. So that's what the theorem and the converse is all about. If this is true, it means it can also be true that because I want to get to that point, I will have to travel this distance. So that's what we're going to be talking about with this particular thing. Now, the key words here is we have what you call a perpendicular. Remember, we've been looking at this in the previous grades. Perpendicular, we normally use this sign, right? It means that they make 90 degrees with one another. So if I say these two lines are perpendicular, it means there is a 90-degree relationship between the two lines. That's what perpendicular is about. Bisector would then mean, bi means two, right? So bisector, it means the line is cut into two equal parts, right? Into two halves. So if this line is bisected, my line AB is bisected by M. It means that AM is equals to MB. That's what bisector means. Then midpoint, same thing as what I just spoke about. So bisector is what cuts it, and then that point where it is cut into two equal parts is called the midpoint. Now we have what we call inductive reasoning, guys. Remember, inductive reasoning is based on trying to see whether this is always true or not. We are trying to induce and see exactly whether this will always be the case. The big question for you: are our conjunctures always true or not? We don't know. Only based on proof can we then make the claim that they will always be true or not. The condition must be this or not. So that's what we need to talk about. What if we change the size of the circle? You see, that's what I'm talking about. To say the condition, if we then change the size of the circle, does that make the conjuncture to still be true or not? Does it then change it or become something else? That's what we need to be thinking about in trying to do Euclidean geometry. We also have deductive reasoning. Based on something that we already know, we go back and try and talk about what is the truth of the matter. Now, our theorem is to say the line drawn from the center of a circle perpendicular to a chord, it bisects the chord. And then if you were to be asked a question and you're trying to use this theorem, your reason is normally line from center perpendicular to chord, right? So the condition is if it is drawn perpendicular to this chord here, then the chord is bisected, right? It is cut into two equal parts. So what do we know? We are given the circle with center O and line OP, as you can see on the board. Line OP lies on the radius, though I did not complete it until the last point, or the point on the circumference. And then this is perpendicular to chord AB, right? Now, I don't know, guys. See, one thing I can tell you now is, if I did not tell you, you do not claim it. Euclidean geometry is that. You know this thing that they normally say, monkey see, monkey do. You know when you go to the zoo and you're looking at monkeys, what you do is they always gonna try and do it. We don't do that here. Because it looks like it, it does not make it it. I need to tell you that this is the case for you to then claim. So I need to tell you that I have a center, and also the center is perpendicular. Then you can claim that, yes, the line is bisected. Or I need to tell you that there is a center, and the line from it passes through the midpoint. Then the conclusion will then be it is perpendicular. So I need to tell you, you don't make claims without being told a key word. So, and also one thing, I always see people doing Euclidean geometry and they think, I thought this was not important. There is no way I will waste my ink and write things on the paper that I give you as a question paper maybe, and there is nothing important there. Everything that is there is important. You just need to know and think about it and see where to apply it. So, monkey see, monkey do does not apply. Because it looks like it, it does not make it it. Please note that. Now, what we are required to prove, also by the way, they normally use RTP. You will be seeing a lot of it in maybe your textbooks or later on when we try to do this. I'm required to prove that this is equals to that because of that 90 degrees there. So my proof will be, firstly, there's what we call a construction. You need to draw OA. You can see there's OA there, and also draw OB there. If you do that, you will then say in triangle AOP and BOP. So the beauty of math is it's a language, right? You're talking to me and telling me where must I focus, right? My focus will be in those two triangles. And in those two triangles, we can see that angle APO is equals to 90 degrees. That's what we were given. But because of it's 90 degrees, angles on a straight line make 180. It means also BPO is also 90 degrees, because that's what we know in terms of angles on a straight line. Then AO is equals to BO. That's the radius of the circle, right? But because it's plural, we normally say radii. Now, I did say that any line drawn from the center to the circumference of the circle will always be equal. So those two lines are equal. And then also, OP is equals to OP. Clearly, it is one side that is common in both the two triangles. As a conclusion, I will then say that triangle AOP is congruent. Remember, this is congruency. Is congruent to triangle BOP. And my reason will be, I proved a right angle triangle, a right angle I proved the hypotenuse side, which is the longest side, and one more common side between the two. Now, what they wanted me to prove was AP is equals to PB. This, I normally use the reason CP, CT, C, right? Now, I will explain. This means congruent parts of congruent triangles are congruent, right? So if I've proven that the two triangles are congruent, it means all the parts of those two triangles will all be congruent as well. Remember, congruent means equal, right? So if I prove that these two triangles are congruent, everything in those two triangles will then be congruent. That's what that CP is, but at times they just use from congruency. You don't need to use those letters there. And then what I then know is, remember with my converse of this is to say, I said if it passes through the midpoint, then it is perpendicular to it, right? But we will look at that at a later stage. But now the big idea here is we were trying to see that if this line, that is my radius, is perpendicular to this line, which is my chord, then the chord will then be bisected, meaning cut into two equal parts. And this is my proof. Because it's a formal proof, there's three things that you always need to do. It's what you are given, what you are required to prove, and then your construction, right? And then lastly, which is the fourth thing, that what you need to try and do, then your proof. Right, so you look at what is it that you are given, what do they want you to do, you construct, because it's a formal proof, and then you start with your proof. And then from there, you will then be done with this. So remember, with a formal proof, there's always a need for you to tell me what did I give you, because that's what determines what you can do, excuse me, with that. Also, what do I want you to do? They're required to prove. 3, do you have sufficient information or not? If you do not, then construct, right? You do say construction and tell me what you did. Lastly, then prove it. Let me let you try and digest that for now. I'll be back with some more after the ad break. Stay tuned. Hi guys, welcome back to the last segment of the show. So we've looked at a lot of things, guys. We started with investigating. We then looked at if that is the investigation, what do we observe? We called it a what? A conjuncture, right? And then from there with the conjuncture, we said, okay, we don't just leave it there because really we are smart people ourselves. So we then go further and say, okay, let's try and prove this thing and see exactly why is the conjuncture always true or not always true. And remember that question I asked you, are our conjunctures always true? No, they are not always true, provided you prove them. If you prove them and you change everything and the proof still holds, then they will always be true, given that you prove them. Now we're going to look at what you call the converse of this and also a corollary of this. But I know I'm throwing a lot of big words, guys. But guys, you really need to know these terms. If you don't know them, just write them down as you're seeing them. Go to your dictionary, your maths dictionary, and look at what they mean so that you can familiarize yourself with them. Because going forward with your maths career in school, I promise you, you're going to be seeing a lot of them, and you need to understand what they mean, right? So far, we've looked at the radius, a chord, twice the radius we said is our diameter. And then we looked at our theorem, which is a line drawn from the center of a chord, of a circle, perpendicular to the chord. The condition is it must be perpendicular to that chord, then the chord is bisected. Our reason, we said, we normally shorten these things, guys. Remember I said the perpendicular is like an upside down T, right? So it's line from center perpendicular to chord. And then from here, the converse of this is to say, if a line now is drawn from the center of a circle to the midpoint of the chord, then the line is perpendicular to that particular chord, right? And then the reason for that will always be line from center to midpoint of chord. And midpoint, we normally shorten it that way. Guys, we are very smart people. We don't really need to show people that we know the English words of these things, because our mind is always about communicating mathematically. So we normally shorten those things. Now we have what we call a corollary. And with a corollary is to say, if all of that is true, then this would then be the case, right? So it means the perpendicular bisector of a chord always passes through the center of the circle, right? And this is perpendicular bisector of chord, which perpendicular like that or perpendicular like that as an upside down T. Now let's just try and prove this and put this into context, right? And see exactly what is it that we need to do. Now, what do we know? We know that in a circle with center O, I said I need to tell you something. The O is the center of the circle. If I did not say this, you don't assume that the O is the center of the circle, please. Excuse me. And then RT is equals to 8 centimeters, right? So this whole length there is 8 centimeters, excuse me. And then OS is 3 centimeters, as you can see, I've shown you. RS is equals to ST, right? RS is equals to ST. So this is equals to that. Very fast cars. RS is in Audi unums and ST will be Ford. And they are competing because they are all fast. But anyways, we are not there. So if those two are equal, it makes this one 4, I mean. It makes this 4 here and it makes this 4 because they are both supposed to add up to 8 centimeters. OB is perpendicular to AC. We know that. They just showed us there. If that is the case, remember, then we can claim that those two are equal. And since they told us that these two are equal, then we can claim that we have a 90 degree there. So far, you can see, I don't know anything about the questions. I am only analyzing the statement. OB is equals to 4 centimeters. You can see it there. Now, as I just said, I don't know anything about the questions as yet. I'm just analyzing the statement. Please stop this thing of always when you open your calculator or anything like, when you open your question paper, the very first thing you want to do is to on the calculator as though you're going to take pictures of the question with the calculator and it's going to solve it for you. No. Read to understand, and then apply what you understand to the diagrams and then go to the questions. Don't read, look at the diagram and you are rushing as the flash to the questions and you don't understand what is happening on the statement and the diagram. You don't do that. So if your diagram looks clean after you answer your questions, then I promise you, you did not do the right thing. You must first make your diagram dirty by trying to apply everything that was said on the statement so that it makes sense. And you will see after doing that, you would have answered a few of the questions already. So please note that. Now, let's try and see what do they want us to actually do. So remember that this is 4, that is 4, therefore this is 90 degrees. So calculate the length of OA, right? The radius of the circle. So OA is the same as OR. It's the same as OT. It's the same as OC. So it means I can calculate any of them, and then at the end I will just claim that OA is equal to whatsoever that I calculated, provided it has sufficient information there. The first thing that I will need to do first will be to say RS is equals to ST, right? Why? This I was given, I was told, Oh, by the way, I will just say this is equals to 4 because they did tell me it's equals to 8 as a total, right? Therefore, I will then say that OS is perpendicular to what? RT. Remember my reason. I said line from center to midpoint, right, is perpendicular to that. So already I know that. Why am I doing this? Is because I am now trying to find OR, because that's where I have sufficient information. So therefore, after claiming all of this, I will then say that in triangle ORS, then I can try and talk about it. I know that I'm going to have OR squared is equals to 3 squared plus 4 squared. Why do I then use theorem of Pythagoras? Why? Because I have a 90-degree angle. Remember, that's what qualifies me to use the theorem of Pythagoras. And then from there, I said it was OR squared is equals to 3 squared plus 4 squared. 3 squared, you know, will be 9 plus 4 squared is 16. This is equals to 25, right? And that's OR squared. Then my OR will be equals to 5 centimeters, right? Therefore, OR is equals to OA is equals to 5 centimeters. Reason, radii. Please, you don't make claims and not give me reasons for them. Then I will just quickly make it incorrect, because we don't make baseless accusations in math. Then calculate the length of AC. So now I know that this length here is 5, right? Now they want me to find the length of AC. With AC, I can find AB, because that's where I have sufficient information, times it by 2, it gives me AC. Firstly, why will I need to do that? Firstly, I claim, right? I say that OB is perpendicular to AC. And what is this? We were given this information. Since this is the case, we can then say that AB is equals to BC. Why? It is line from center perpendicular to chord, right? That will be my reason. Remember when we were looking at the theorem, I said that's the reason. And then from there, I can then talk about in triangle. I said this is a language, guys. You don't just write things and then I need to wonder where this comes from or something like that. You treat me as a person who does not know anything. You communicate with me and tell me, look here, look here, look here, so that I can see all that you are saying. I will then say that AB squared is equals to 5 squared minus 4 squared. Remember, it's the theorem of Pythagoras, and this will be 5 squared, we know that is 25, minus 4 squared will be 16, and then if that is the case, 25 minus 16 we know is 9. Right, let me just go to the other side. So we are now on AB squared is equals to 9. It means that AB is equals to 3. Therefore, AC will then be equals to 6 centimeters. And that's where I leave it. And then, you know, easy peasy, lemon squeezy. Now, let's just look at a summary of all that we've done so far. 1, we said we have a chord and radius theorem. Line from center perpendicular to chord. If a line is drawn from the center perpendicular to the chord, it bisects the chord, right? Bisects the chord. Also, the second one, which we said was the converse, if a line is drawn from the center to the midpoint of the chord, the conclusion, okay, so let me do this. Conclusion. The conclusion is that it is perpendicular to that chord. Lastly, a perpendicular bisector of a chord, what does it do? It passes through the center of the circle. So far, guys, we've looked at the concept of the radius, the concept of a chord. At a later stage, you will see we'll look at other things in terms of the concept of circle geometry, and that's what is important. So, remember the big thing here. You do not make a claim unless, one, the statement gave you a clue that this is the case. So I tell you center O. That means I have a center. I don't mention a center, you don't talk about a center yourself. Number two, you don't make a claim if you cannot prove it, right? You make a claim based on the theorem because the theorem was proved. By the way, you saw that the theorem that I was using, I was not proving it. Why? Because it's already a theorem. I was just trying to show you where it comes from. So not that every time I use the theorem, I need to start by proving it and then use it. No. Already it's been proven and it's been claimed to be a theorem. I just use it because why? The given information does qualify it to be a theorem, and for me to claim that this is equals to that, that is this, that is 90 degrees and all of that. So make sure that you understand those. Also, please know the difference between a theorem and its converse. If this is true, that can also be true, right? Based on this and that. I know I'm saying a lot of this and that, but I hope you understand everything that I've said so far. Guys, from me to you, remember, mathematics is food for the soul. I will see you next time.